I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on a Newton's second law experiment called a modified Atwood machine. All right, so what an Atwood machine is you have a pulley and you have a rope over that pulley, and you use that to, farmers use an Atwood machine to lift bales of hay up into the hay loft. So you have a weight pulling and the pulley system pulls it up. So we've modified that. So we have a hanging weight off of the end attached to a car that is horizontal. So we have this weight that is going to cause this car to accelerate. So we're going to go ahead and make some observations. So go ahead and pause the video, write down all your observations that you saw, and we're going to go ahead and show you what some of my students have made in terms of observations in the past. All right, so you can see some of the observations that my students made, and hopefully you made some of the same observations. The car sped up. Okay, so the car sped up. So what we're going to do is we're going to draw a free body diagram for that car as it speeds. So let's go ahead and pause the video, draw a free body diagram for that situation. So the first step in drawing the free body diagram is drawing this. What we're going to do is we know that the string is directly in contact with the car. That supplies a tension force. We know that the ramp is in contact with the car. That supplies a normal force. And we've done something to modify the situation so that there is no friction. So we actually canceled out friction. And we know that the earth supplies a gravitational force. And notice that the weight, the hanger does not have any interaction with the car. We know that the hanger and the string have an interaction, which is a tension force, which is the same tension force as we have up here. And then we also know that the earth supplies a gravitational force on the hanger, and the ramp is not in contact with the hanger. So we're also going to draw a free body diagram for the hanger as well. And we have three forces that are acting on it. We have the tension force, we have the gravitational force, and we have the normal force. So we know that the normal force points up and the gravitational force points down. And from the video, you can see that the tension is pulling to the left. And for the hanger is accelerating downward, which means that we have this gravitational force on the hanger, but the upward force of tension is going to be smaller because it is accelerating downward. Okay, so we have this acceleration going on for our free body diagrams. We can see the car is accelerating, and we can see that the hanger is accelerating. All right, so we could see the free body diagram. So one thing that's always a question is there friction? Is there not friction? So what I have done in this situation is to help balance out friction. This ramp is set such that when I push this car towards the pulley at the end of the ramp, that it moves at a constant speed. So that way I know that when the fishing line is pulled taut with the hanging weight off the end, I know that that is the only force that is causing it to accelerate, which is what we're looking for. Okay, so some of the observations we can make. So let's go ahead and let's go to the whiteboard. All right, so here's some of the changes that we can make. Is the mass of the system, the weight of the hanger, and we can measure or calculate the acceleration. So in this video, what we're going to do is we're going to change the weight of the hanger. Now notice I keep saying weight and not mass. So the weight of the hanger, is the force of gravity that is acting on the hanger, which is causing the entirety of the system to accelerate. So to calculate the weight of the hanger, you need to know the mass of the hanger, and you're going to multiply that by g. And in this case, we're going to use 9.8 because the acceleration due to gravity, we want it to be an exact value in a lab situation.
So the mass of the hanger, we are going to start with a 5-gram mass, and we're going to go all the way up through 50 grams. So 0.005 kilograms to 0.05 kilograms. And we're going to increase that by increments of 5 grams each time, which means if we're changing the weight of the hanger, that means the mass of the system has to be a control. Well, the mass of the system being a control, that means I have to take whatever I take off of the car, I have to put on the hanger. And whatever I take off of the hanger has to go on the car. So the mass of the system, the car and the hanger, is the same. So what I'm going to do is, since the system mass is a control, the system mass, I'm going to make the car 1 kilogram by itself. So the mass of the car with one mass on top is 1 kilogram. And the overall hanging mass is going to be 50 grams, or 0.05 kilograms. So that is going to be what I'm going to shift around, is those 50 grams. So the overall mass of the system, which is going to be the mass of the heaviest hanger, is going to be 0.05 kilograms. So that means my system mass is going to be 1.05 kilograms, and that is going to be my controlled value throughout the experiment. And then we're going to go ahead and calculate the acceleration from using the kinematic equation that we derived for acceleration earlier.
All right, so we can see that one set of groups is going to be working on one particular lab, where we are going to keep the mass of the system, which is the mass of the system is included the car and the hanging weight. We're going to keep that at control. And what we're going to do is we're going to change the amount of weight that we have on the end of the hanger. And the way we keep the system mass at control but change the weight on the hanger is whatever weight comes off of the hanger has to go on to the cart. So we have to make sure that we're constantly moving weight from one place to another to make sure that we're not changing the mass of the system. And the other sets of groups are going to check and see, change the mass of the system, but keep the weight of the hanger exactly the same. So what we're going to do is, in that case, we're just going to keep adding mass to the car. So that way, if there's more mass added to the car, then the weight of the hanger stays the same. So we're going to make a hypothesis for each of those. So whichever one you have, go ahead and pause the video and make a hypothesis statement as to how you feel the acceleration is going to change based on those changes, changing the weight of the hanger or the mass of the system. All right, so for this video, this data collection, what we're going to do is we're going to do the low-tech version, where we don't have any of these fancy gadgets and sensors that we're going to use. So what we need to know is that this cart is going to travel in the direction and accelerate until the mass hits the ground. So what we need to know is that the mass is 0.91 meters above the ground. If we know that it is 0.91 meters above the ground, what we're going to do is we're going to use kinematics and we're going to calculate the acceleration. So we're going to go to the whiteboard and we're going to see how we're going to do that.
All right, so what we're trying to find is the acceleration of the hanging mass cart system. So the information that I know is about the hanging weight, and the hanging weight is 0.91 meters above the ground. It hits the ground. It starts from rest, and what I'm looking for is the acceleration. So of the variables I have remaining, I have the final velocity that it hits the ground with and the time. Of those two variables, the easier of the two to find would be the time, because we can just use a stopwatch to calculate the time. So what we're going to do is we're going to use our kinematics and an equation that does not have our final velocity in it. And if you're using your AP formula sheet, the AP formula sheet has the second kinematic equation. Now, because it's accelerating downward, I changed that plus 1/2 AT squared to a minus 1/2 AT squared. So now what I'm going to do is I'm going to solve for the acceleration. So I know that the Vy naught times t is 0 because my initial y velocity is 0. So 0 times t gives me 0. I also know that my initial height is 0.91 and my final height is 0. So I'm going to change that to negative y naught equals negative 1/2 a t squared. And I'm going to multiply both sides by -2, and then I can solve for my acceleration. So when I'm done collecting my data, I'll have a bunch of time data. And what I'm going to need to do is I'm going to take that time data and I'm going to use this equation here, and I'm going to solve for the acceleration. So I'm going to convert times into acceleration, knowing that it falls 0.91 meters, and I will collect the time values in order to calculate my accelerations. All right, to recap, what you are going to collect is you're going to change the weight of the hanger, and you are going to calculate the acceleration. From that, you're going to end up with a data table that has time in seconds, and from that you're going to use the kinematic equation that we derived to calculate the accelerations in meters per second squared. And you're going to have masses of the hanger that you're going to convert to kilograms, and then from that you're going to multiply by 9.8 for each of those masses, and you're going to find the force of gravity on that hanger, or the weight of that hanger. And what you are going to graph are these two columns. And you are going to create a graph with the weight of the hanger on the y-axis and acceleration on the x-axis. And the reason for that is when we graph it this way, the slope has more meaning to us in this way. It's easier to figure out the meaning of the slope when we graph it in this fashion. So go ahead and collect your data. Remember, you're going to measure the time it takes for the hanger to fall. You're going to change the mass of the hanger in terms of kilograms, and you're going to calculate acceleration and the weight of the hanger from each of those. And then you're going to produce a straight line graph and find your mathematical model.
All right, so now it's time to run some trials. Let's go ahead and collect your data. So due to the length of this video, we're going to go ahead and look at the lab results in a different video. So I hope you have a great day and an even better tomorrow. If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter @CaviCoaches.